Hello. The case 2 is end-fire array, in which we consider an array of n number of isotropic point sources with equal amplitude but opposite phase, and the spacing between the elements is same. So there are two cases in end-fire array. One is called as ordinary end-fire array because the directivity and gain provided by this antenna is low, so it is called ordinary end-fire array. And then the second case is end-fire array with increased directivity. So in case of end-fire array, you can see, since the phase between two elements is not same, the value of delta cannot be 0, but we need to compute it. In previous case, if you see, the value of delta was 0 because there was same phase between the two elements, and that indicates the value of delta, which indicates the phase of adjacent elements, is equal to 0. But now it is not 0, but we need to compute it, and in order to compute it, we make use of equation psi, which is dr cos phi plus delta, and we substitute the value of psi is equal to 0 because from array factor equation the maximum field can be obtained when the value of psi is equal to 0. Thus, from above two conditions, we have value of psi is equal to 0 and the value of phi also 0 because we are considering cos, and in case of cos, the phi value being 0 gives us the maximum value. So the equation modifies to 0 is equal to dr. Dr will be any value that we consider later of d. So dr we keep as it is, cos 0 plus delta. So cos 0 is 1. So we get 0 is equal to dr plus delta, which makes the value of delta equal to minus dr. Now this is a very typical case of representing an end-fire array, that in case of end-fire array, the value of delta is always minus dr, and in case of broadside array, the value of delta is always 0. So from equation 1, which is delta is equal to minus dr, we understand that an end-fire array, the phase between sources delta depends on the distance between the sources in radians, that is dr, because its value is minus dr. So if you assume that the spacing between the two elements is lambda by 4, then you know this the value d in meters, it is lambda by 4. So how we compute dr is 2 pi by lambda into d. So 2 pi by lambda into lambda by 4 gives us answer pi by 2, that is 90 degree. The above calculation shows that for source 2, there is a phase lag compared to source 1 by 90 degrees, and again similar way source 3 is lagging by a 90 degree with respect to source 2, etc. So it continues for all the n number of elements. So we can see the kind of radiation pattern we get because of this arrangement. If we consider 4 isotropic point sources, n is equal to 4, here it is shown with d equal to lambda by 2, we get a radiation pattern which is quite broad and its maxima is in the direction of phi. So you can see the maxima currently is in the same direction in which the elements are placed. That's the difference between the broadside array and end-fire array. In previous case, the broadside array we saw was having maxima in the direction perpendicular to the axis on which the elements are placed. So this is ordinary end-fire array. Now ordinary end-fire array produces low directivity, so there is a modification done by researchers in order to get improved directivity or increased directivity, and that is our case number 3, end-fire array with increased directivity. Now we can see the modification done is in the term delta by adding a term pi by n. So our previous term delta, which was minus dr, now becomes minus dr minus pi by n, where n is number of elements. So if you take minus common outside the bracket, then it is dr plus pi by n. This gives us improved directivity or increased directivity, and the phase difference psi is now becomes dr cos phi plus delta, where delta is minus into bracket dr plus pi by n, which is given by equation number 1. Now in order to compute the maxima and minima and null, we have to take an example here of 4 isotropic point sources, and the separation between two elements is lambda by 2. So D is lambda by 2, and we know for D lambda by 2 the value delta we get minus 5 pi by 4, and the radiation pattern that we get is as shown in this figure. Okay, so this concludes our discussion on end fire array, that in case of end fire array, if we improve the directivity, the size of major lobe reduces and that increases the directivity. So with this we conclude unit number 1. Thank you.